Hi, this is Professor Dorr, and this is EE310 lecture number 23, Complex Poles and Convolution. In this lecture, we're going to cover the end of section 15.4 and all of section 15.5 in Alexander and Sadiku's textbook, Electric Circuits. Now, when you studied Laplace transforms in your math courses, you might have walked away with the biggest take-home message of you can solve differential equations using algebra instead of calculus. And that was kind of a nice thing back then. But one of the reasons I enjoy working with this material and teaching this material to you guys is we can do a lot more than just solve differential equations with algebra. We can solve all kinds of cool problems with circuits and acoustics and mechanical systems, and we can put not only unit steps into circuits, but we can put triangle waves and sawtooth waves and waves that look like little tortoise shells and Beethoven's Ninth Symphony through circuits and systems. And we're actually going to go into that a little deeper in the next lecture where we're going to talk about acoustics, but I'll get to that in just a second. So as in all of my Laplace Transform lectures, I'm going to rely heavily on my Laplace Transform Roadmap. And that way you'll be able to take the information that we talk about today and keep it in perspective of this larger picture. You might remember that in our first lecture on Laplace transforms, we did Laplace transforms, one after another after another. We went from time domain to frequency domain with signals. Then in the last lecture, we learned how to go from the frequency domain to the time domain. And that's the inverse Laplace transform. And of course, what we did is we took big complicated expressions in the frequency domain. We broke them up into little Lego building blocks. And then we used the linearity property to get little inverse Laplace transforms. And then we also did a little problem where we actually took a unit step all the way through a circuit and out the other end. So we are going to keep using the Laplace Transform Roadmap. The first thing we're going to do in today's lecture is we're going to learn how to do this inverse Laplace transform with complex poles. But then the bigger thing we're going to do is we're going to explore this path called convolution. We're going to discuss the impulse response of a system. You can see it's on the Laplace transform, and it's very important to what we're doing, but I'm going to give you a good intuitive feel for the impulse response. And I'm going to show you how it's more than a mathematical concept. It's a really useful and practical thing. Would you like to hear an impulse? Here, there, you just heard one from an engineering sense. All right, we're going to present the convolution integral. And as we present the convolution integral, you may remember that there's time reversing and shifting going on in the convolution integral. Let's make that practical. Let's take that time reversal, and instead of leaving it as a mathematical concept, let's convert it to the idea that if you have a signal that goes like this from time equals 0 to time equal infinity, if you want to put it into a circuit, you got to turn it around so the beginning goes in first. And that's going to give you some an intuitive feel for why that time reversal is in those equations. Hopefully it's really going to help you. We're going to do a problem where we are going to first do it graphically. We're going to do the convolution problem graphically, and we're going to wave our hands and kind of sketch out what the response should be. Then we're going to get down and do it with the integral. So you're going to see it both ways. We're going to wrap up the lecture with practical convolution. Basically, we're going to whack a pipe with a pencil, and it's going to go ding, 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 and we're going to relate that to all the math that we're doing. So we're going to show you how the math describes the convolution, the math describes the intuition, and how the intuition supports the math. Now, in the next lecture, we're going to do even more practical examples because this stuff is just too good. And I want you to walk out of my class with a good intuitive understanding of this. Even if you can't repeat the convolution integral, I want you to know what it means. And we're going to do that a couple of ways in the next lecture. One thing I'm going to do is relate convolution to a finite impulse response digital filter, an FIR digital filter, because that's really what an FIR filter is. It's a convolving machine, so why wouldn't I present it to you in these lectures? The other thing we'll do in the next lecture is we're going to do analysis of music venues. So we're going to look at music venues from sleazy bars with cinder block walls to a beautiful big 16th century church. We're going to do fun things. We're going to use our Laplace transform to take Louis Armstrong on his trumpet and have him play in the 16th century church. And you'll see why people didn't play jazz in the 1600s. So it's a really fun lecture. A lot of my seniors end up coming back and checking out this lecture again because it's really just a lot of fun. We're going to start this lecture by going over how we deal with complex poles, which is the last little piece of section 15.4. So if you've stumbled across this lecture looking for information on convolution, you might want to skip ahead to that. So what we found was that transfer functions can have three kinds of poles. They can have simple poles, which look like this. You've got a numerator, and you've got an s plus p1, s plus p2, where p1 and p2 are real values. And we found that we could use the residue method to get our A1 and A2 values pretty easily. We could also use the method of algebra. So that's our first type of pole. Our second type of poles are repeated poles. And these are poles where the pole is just squared or cubed or something like that. And we found in the last lecture that the residue method gets a little bit ugly here. And at least for me, I really prefer to use the method of algebra here. But now let's look at the third kind of pole that we can encounter in a transfer function. It is a quadratic or a complex pole, where we have our numerator, and then below it we're going to have s squared plus as squared b plus b. Now, something that I want to remind you is this function right here, just because you see a quadratic doesn't mean that it's a real complex pole, because you may be able to factor this and find that it's really just s plus p1 times s plus p2, and p1 and p2 are real values. So be careful about that. What I do whenever I see a complex pole as part of a transfer function is I always shove it into the quadratic formula really quickly and determine if it's complex. Of course, I don't have to do the whole quadratic formula. I just do the b squared minus 4ac part and see if that's negative, because that's what's inside the square root. So be careful with that. And I'll make sure I do it in these examples so that I keep reminding you. Now, in our last lecture, we talked about guarantees. And we had a guarantee for our simple pole. Or in other words, we were guaranteed that this part of the transfer function could be represented by a1 over s plus p1 plus a2 over s plus p2. That's our guarantee. And the beauty of that guarantee to me is from that equation, from our guarantee equation, we could just solve for A1 and A2. We had another guarantee for repeated poles. It was a different guarantee, but it was a guarantee, and we can again use the guarantee equation to calculate those unknown values on the right-hand side. So now we're going to look at the guarantee for complex poles. And let me just remind you, if you are going to be able to use a cheat sheet on your exam, write down your guarantees, because those are going to be your roadmap through this partial fraction process. So we've got a complex pole, and that's what we're going to do in the beginning of this lecture. Here's the guarantee. F of s is going to be equal to a1s plus a2 divided by s squared plus as plus b plus the remaining part of the transfer function that doesn't have the complex pole pair. Or in other words, if we have a transfer function like this, we know that it can be broken up like this. And of course, the F1s, let's elaborate on that a little bit. A transfer function might have the complex pole multiplied in the denominator here by a simple pole. And if there was a simple pole multiplying this, F1s here would just be some constant over s plus p. So we call it the remaining part that does not have the complex pole pair. So this is your guarantee. This is the thing you want to write down on your cheat sheet. So what I'm going to do is I'm going to focus on the quadratic pole. That's why I put this little symbol here, and say that we're going to convert our quadratic pole here, or set of poles, I guess, into this format right here. So our guarantee says that we can make it look like this. And now what we're going to do is we're going to use a little bit of algebra to make it look like this. Why are we going to do that? Because these are right in the Laplace transform table. So this is the kind of Lego building block we want. Because once we get it into this formula, we go into the table and we just invert it by inspection. So once we get our f of s into this form, this inverse Laplace transform is easy. F of t equals all this stuff here. Don't forget that f1t. Remember, it came from our f1s. So what's the deal? We see a transfer function. It has a complex pole pair. We make sure it's really a complex pole by looking at the discriminant of the quadratic formula. And then we have our, we use the method of algebra to get our A1 and A2. And then we're going to use some additional algebra to get it into this form here. And then we're going to pop the answer out right out of the table. So here's that strategy. First, we solve for A1 and A2. We use the method of algebra. I do anyway. Next, we solve for alpha and beta. You notice alpha and beta didn't exist up here. We got to calculate them. And then finally, we're going to solve for this little B1 that's sitting over here all by itself. So you might recognize that solving alpha and beta here, solving this function, s squared plus as plus b, into s plus alpha squared plus beta squared is really just the technique of completing the square that you learned in algebra. Now, completing the square is way too difficult for me. So what I do is I just go back to first principles and calculate it out. Here's the deal. I know I've got an s squared plus as plus b, and I want to make it look like s plus alpha quantity squared plus beta squared. So I got an s squared plus as plus b equals s plus alpha quantity squared plus beta squared. So what I'm going to do is I'm just going to solve it. And I'm going to do it by just equating coefficients. So let's see. On this side up, I have an a times s. And on this side, when I multiply it out, I have a 2 alpha. All right, so 2 alpha is equal to a, or alpha equals a over 2. So now I'll kind of do the same thing over here with my little dotted line, and I'll say this is an s squared term, this is an s term, this is an s to the 0 term. I go down here, got to be equal to alpha squared plus beta squared. So I can see that b equals alpha squared plus beta squared, and I solve that for beta, and I get my handy dandy little formula here for beta. And the book used the completing the square technique, which is a very good technique to do it. Too hard for me to remember. So what I do is just go through this little derivation when I need it. But then, if you're in my class, you write this down on your cheat sheet and you use it during the exam. Because on my exam, I don't care whether you know how to complete the square. I want you to be able to just use these. So put these rascals on your cheat sheet, use them, get out of my class, hit the flush lever, and forget them. And just remember that you can figure this crap out whenever you need to. Now let's solve for B1. Let's go back and look at where it was again. Remember, we started off with this. We got our A1 and A2 with the method of algebra. And then we got we started out with this. We got our A1 and A2 with the method of algebra. We just got our alpha and our beta. Now we need this little B1 term. So looks like all we got to do is just equate these some numerators. And here are the numerators that we want to equate. We know that f of s is equal to this expression here. So we're going to just equate these two numerators, this one and this one. And here they are. We equate them, and looks like we get a little canceling out here, and we solve for our beta 1 value. Here's a nice little formula. I put a box around it so you can put it on your cheat sheet. All right, let's look at an example. So in this example, I have a transfer function, and I can see that it consists of a simple pole and I'll call it a quadratic pole, because I don't know if it's a complex pole, but I'm just going to call it a quadratic pole. And the first thing I'm going to do is throw the quadratic formula at this equation right here. Why do I do this? The reason I do this is because I want to make sure that this is really a complex pole. Because for all I know, this could be factored down to s plus 1 times s plus 5 or something like that. And if that was the case, I'd have 3 simple poles, and I wouldn't be going through the procedure we just did. So I throw the quadratic formula at this. I know a lot of you sing that little song for the quadratic formula. I always get a kick when some student does that in my class. But what I can see in my discriminant is I have 8 squared is 64 minus 100. Discriminant is negative. So I definitely have a complex solution because we're going to have a j in here when we get this square root of a negative number. So I'm going to throw my guarantee at it. And this equation here is the result of my guarantee. Or in other words, I started with this. My guarantee said I could do this. Let's look up where we made that guarantee. Here's the guarantee. If I can represent it like this, it's going to be a1s plus a2 over my quadratic plus the remaining part that does not have the complex pole pair. Let's make sure we see where that goes in here. So here is my complex part, and look, here's my a3 over s plus 3. And here I use my guarantee for my simple poles. So given this equation here, I'm going to just equate this equation and this equation. And here it is. Here's my 20 over s plus 3, yada, 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 equals a1s plus a2 plus my a3, all this stuff. But what I do, you can see I'm putting this over a common denominator. I'm doing that so I can equate my numerators. So I got to multiply the a1s plus a2 times s plus 3, and I got to multiply by a3 by the quadratic. And I do all that here. And now, with my common denominator, I can say, goodbye, denominator. I want to equate these numerators. And again, this is kind of a weird trick for you because you look at this and say, hey, you got one equation in 3 unknowns. But really, by equating the coefficients, I'm going to end up with 3 equations and 3 unknowns. Maybe stop the video, get a cup of coffee, make sure you're cool with that, because this is a really, really powerful technique. So let's look at the numerators. I know that my s to the 0 terms have to add up to 20 over here. And my s to the 1 terms and s to the 2 terms, they got to add up to 0 because I don't see anything here. So let's multiply things out here. And I multiply them out. I get a whole bunch of stuff. And then I gather up my s squared terms, my s terms, and my s to the 0 terms over here. And now I get excited because I get to write 3 equations in 3 unknowns. And I say, I got no s squared terms. So that means I'm going to have a1 plus 0a2, right? There's no a2 here, plus a3 is going to be 0. Or in other words, the coefficient of all these s squared terms is 0. Now let's go to my s terms. And I have 3a1 plus a2 plus a3. Why did I change the order? Because I'm going to drop them into a matrix. And that equals 0 also. Now let's go to my s to the 0 terms. 0a1 plus 3a2 plus 25a3 equals 20. I shove that into my matrix. I use my calculator, and out pops a1, a2, a3. Now remember, I did this all in one big fell swoop here. And that works for me. It really wasn't that hard. So now I can say that this function that I started with ends up looking like this because my guarantee told me this form would work. And then I used the method of algebra to find the constants that fit into the form. All right, so now I've got my, I'm going to focus on my quadratic term a little more. Remember, I know it's not just a quadratic term, it's a complex quadratic. So let's see, s squared plus as plus b, I'll say a equals 8, b equals 25, and A1 is equal to -2, and A2 is -10. I can see those here. So let's go through the completing the squares business to get alpha and beta, because that's where we want to go next with this equation. Or in other words, we want to go, we have this. We now want to get the equation into this form. So we're going to need to get alpha and beta and then beta 1. So we're here right now. We need to go down here. So in order to get alpha and beta, we need to complete the square. And I'm just going to use the equations I derived on page 2, and they're sitting there on my cheat sheet, so I'm going to use them on the exam also. I get alpha equals 4, I get beta equals 3. Bang, I'm done. And then I'm going to also use my equation for beta 1, and it's going to give me -2/3. And I will, from that point, I'm going to say the inverse Laplace transform is easy. I just have to shove all these coefficients into this equation here. Why is it easy? Because this is sitting right there on the Laplace transform or the frequency domain side of your table. And so you just equate these coefficients over here to get the time domain. So here I go. I shove that in there, and here's my general form, and here is my form with all the constants put in. Don't forget that F1t. Remember, that was our simple pole. It is right here, 2 over s plus 3. Don't forget that. F1t, F1t, and we are done. Before we get into the details of the convolution integral, I want to give you some intuitive background on what it really does for us and why we use it. And in order to do that, we're going to look at impulse response, because the two are really tightly coupled together. So the definition here is going to say that the convolution integral allows us to determine the response of a system to an excitation x of t, knowing the impulse response of the system h of t. Let's look at it on the Laplace Transform Roadmap. Here's going to be our input, our time domain input. We'll call it x of t. And we know what's called the impulse response of the system. So we're going to perform this thing called convolution, and we're going to get the response of that system. So convolution allows us to determine the response, y of t, to an excitation, x of t, knowing the impulse response of the system, h of t. So what you've seen in the last lecture is we got the response of the system going this way. We said, here's a time domain input. Let's get its Laplace transform. We'll multiply the Laplace transform of the input times the transfer function. We'll do the inverse Laplace transform, and we'll get V out. And that's a nice way to do analysis. But circuits don't know how to do Laplace transforms. Those just exist in our heads. Circuits are going to just perform this convolution that we're going to go through. So I can get the answer going this way: in, down, over, up, and out. Or I can do it the direct route. We're going to start here and go right through to the output. And that's what convolution does for us. But in order to do that, we need to know the impulse response of the system. So let's measure the impulse response of a system. What is an impulse? It's a unit energy, zero time duration, quote, pulse. So it has a fixed amount of energy, but it's infinitely small, so it's infinitely big. So as engineers, we say, well, we can't do infinitely small and we can't do infinitely big, but we can do pretty small and pretty big. How small and how big do you need it? That's the beauty of being an engineer. Those are the kind of calls we make. So a good approximation to an impulse for me is just a whack, right there. Because it's very short and it has a fairly decent amplitude. So let's measure the impulse response of a circuit. Here's a circuit right here, and we need an oscilloscope to do it. So what we're going to do is we're going to generate a really narrow pulse. And that pulse, we could generate it with a pulse generator. I mean, heck, you could generate it with a 555 timer in the monostable mode. Remember, how small do you want it? We're engineers. So the other impulse is I could take a microphone and put it right here and go, there's your impulse. It's a great impulse. It's going to go into the circuit and we're going to measure the output on the oscilloscope. Impulse went in, impulse response went out. Let's sing it. We can go for our input, and then our circuit is going to be thuddy or boingy. And let's sing this one. Looks like it's a boinger. Ding! Hear the output? Ding! Think of the copper pipe hanging from your wind chimes. I'm going to hit it with an impulse. Ding! And down it went. So I can measure the impulse response of a circuit. And that is this thing right here, impulse response, h of t. So yeah, I just noticed that I'm missing a parenthesis on my h of t here. Oh well, got to fix that someday. But now I want to look a little deeper at my Laplace Transform Roadmap. Namely, we're going to explore this cool arrow right here. What's the Laplace transform of an impulse? Go to the table. It's 1. There's no s. The Laplace transform of delta of t is 1. So let's go down this path. So if I want to get the impulse response in the frequency domain, that would be right here. All I have to do is take my impulse, get the Laplace transform of it, and multiply it by the transfer function. But the Laplace transform of an impulse is just 1. So the impulse response of my circuit or my system is simply its transfer function in the frequency domain. Let's do that again. So we hit our circuit with an impulse, and it went ding, and here's our ding right up here in the time domain. Now I want to look at that in the frequency domain. So what I'm going to do is I'm going to take my impulse, take its Laplace transform, it's 1, multiply it by the transfer function, and now I have my impulse response in the frequency domain. So what that means is that if I take the Laplace transform of the impulse response, I get the transfer function. If I take the inverse Laplace transform of the transfer function, I get the impulse response. So I really want you to see that relationship, and that's why the impulse response is so important. We're going to use it quite a bit in the next lecture, where we're going to compute the frequency response of music venues. But for our purposes right now, we just want to know what the impulse response is. Always nice to know how to get it because we're engineers and we can't sell it if we can't get it. And then we're going to look at how it's used. So here's one way to get the impulse response. We measured it directly. Let's look at another way to get the impulse response. I'll give you a second to just think about it. Look at the roadmap. Here's another way to get the impulse response. Let's compute the transfer function and then take the inverse Laplace transform. Get your transfer function, compute your inverse Laplace transform, you get the impulse response. Let's do it. Here's our little RC circuit. H of S is equal to 1 over RC times 1 over S plus 1 over RC. That's an easy inverse Laplace transform. And it's just 1 over RC, e to the minus t over RC, h of t. That's the impulse response. Now you have to be a little careful with this one because if I hit it with a finite duration, obviously the response at 0 here is going to be 0, not what's shown here. And the difference is that in this case, it actually matters that my impulse has a finite time duration. So I don't want you to worry about that at this point. I know that's bugged me quite a bit, and once I learned more about it, I realized that in this case, our approximation doesn't perfectly predict this. But the important thing I want you to see is I can get the impulse response by by doing an inverse Laplace of my transfer function. Hey, I can get the transfer function by doing a Laplace transform of the impulse response. So we are used to getting the transfer function of circuits by looking at the circuit and doing the analysis. What if the circuit was a big black box? Well, what let's do is, let's do this. Let's give it a whack. Let's get the impulse response. Let's compute the Laplace transform of the impulse response. And we just got our transfer function. At this point, we're ready to introduce the convolution integral formulae. And here it is. It's right in your textbook. And what we have is y of t, or in other words, the output of our system as a function of time is equal to the integral from negative infinity to infinity of x of infinity, let's say that's our input, multiplied by h of t minus lambda d lambda. So a lot going on in this integral. We are going to convolve two functions, x of t and h of t, and we're going to create this integral to do it. We're going to create this dummy axis of integration, which is called lambda, and we can show it this way, or we can reverse the functions around and say it's h of lambda times x of t minus lambda d lambda. Of course, lambda integrates out, leaving a function of time as the result, and we have a special operator here for convolution. Okay, so that's a nasty looking integral. It's got a lot of stuff going on. It's got this dummy axis or dummy axis of integration, which is lambda, and we've got this time reversal going on with t minus lambda. It is not a pretty thing. So what we're going to do is we're going to break this integral down so that you can actually get a feel for what it really means. And the best way I know to do that is graphically. And once you understand it graphically, then you'll see it the way I do, which is through the lens of a finite impulse response filter. And that sounds a little far-fetched right now, but hang with me and you'll get it. So before we go into this more, I want to look at this whole business of time reversing and shifting functions. This is an area that can give some students problems. It's just hard for them to visualize it. I've had the same problem, so I want to just give you a little bit of insight into that. So let's say that we've got a little function x of t. What does x of t minus lambda look like on the lambda axis? Okay, so remember, when we look at this, we're normally used to seeing x of t, where t is the x-axis, or the horizontal axis. But here, I want to plot that. I want to plot x of t minus lambda on the lambda axis. The reason I'm going to do that is because this integration occurs on the lambda axis. So what I want to do is give you an intuitive feel for the lambda axis, but we got to see what x of t minus lambda looks like on that axis. So here's a function. And I'm going to say that it's a function of, and I'm just going to say a dot. So in other words, it's a function of whatever is in the parentheses. This is our dot axis. It's not x, it's not t. I'm just going to call it dot for now. But I can see that if the dot is equal to 0, my function is 0. If the dot is equal to 0.5, then it's 0.5. And if the dot is equal to 1, then it's equal to 1. Or in other words, our function x is a function of whatever is in the parentheses. So now what I want to look at is the time reversing part. Let's look at what x of minus lambda looks like on the lambda axis. So my function that I'm going to plot is x of minus lambda. So when lambda equals 0, x of minus lambda is going to be x of 0, and I'm going to get 0. So here's my first point. Now let's get lambda of negative 0.5. So I want to find the value right here. So x of minus lambda is going to be x of negative 0.5, or x of 0.5. X of 0.5 is 0.5, so I'm going to get my next point right here, 0.5. Now, let's say lambda is equal to negative 1. So x of minus lambda is equal x of negative 1, or x of 1. So our dot equals 1, and it's 1. And what we've done here is we have reversed around the our axis, around our vertical axis. So what we did by putting this negative lambda instead of lambda is we just switched it around. We moved it around to the other side. We reflected it. So that's how we handle the minus lambda. Now, let's look at how we're going to handle x of t minus lambda on the lambda axis. So in this case, we are plotting a function of lambda. We're plotting t minus lambda, but since this axis is lambda, t is going to be a constant. So let's look at x of t minus lambda when t is equal to 2. So we're going to plot x of 2 minus lambda. So we'll say that lambda is equal to 2. So the thing in the parentheses, or my dot, is equal to 2 minus 2, t minus lambda. I'm at lambda equals 2 and t equals 2. So t minus lambda gives me 0. So x of 0 gives me 0. Here's my first point for lambda equals 2. Now let's say lambda equals 1.5. T is going to remain at 2 because t is 2. It's a constant here. And so t minus lambda gives us 2 minus 1.5. So the thing in the dot is 0.5, and x of 0.5 up here was 0.5. So I get this point. Now let's look at lambda equals 1. So t equals 2 minus 1 gives me 1. So the thing in the parentheses is 1, and x of 1 is equal to 1. So here is my third point. So what are we seeing here? Well, we know that our reversal, saying we're going to plot x of negative lambda, that reflected us. But now t is an offset, and that shifted us. So as t increases, the function x of t minus lambda shifts right. So as t increases, you can convince yourself up here, t is just shifting my function right on the lambda axis. So given x of t, we want to place x of t minus lambda on the lambda axis. Because remember, we want to calculate this integral. It could be this integral, but I'm going to focus on this side of it. I could do this one, but I like this one better, and you'll see why. So given x of t, I want to place x of t minus lambda on the lambda axis, so I draw the lambda axis. I mirror image x, and then I shift the mirrored image right by t units. That's the recipe that I get from this silly little argument where I used my dot. All right, so let's do a graphical convolution problem. I like to start these convolution problems off graphically, just so you can see it, and then the integral will kind of tag along. So this is problem 1544b in our textbook, and we're going to start off doing it graphically, and then we're going to do it using the mathematics. So we are asked to convolve f1 and f2. And convolution is commutative. So convolved with f2 is equal to f2 convolved with f1. So for this one, it's going to be easier if I slide my triangle. And you're going to see by sliding my triangle means that as time increases in this expression, it's going to move my x of t minus lambda. So let's visualize our integral. Here is my f1 of t, here's my f2 of t. So what I'm going to do is I'm going to put it on the lambda axis. So let's go back up to our integral. And so I'll plot h, or f2 in this case, directly on the lambda axis. But this x function, or f1, it's going to move on the lambda axis based on this constant t, which is this t, of course, right here. In other words, I'm going to leave my f2 of t just sitting here on the lambda axis. And as t changes, it's going to shift my triangle. So at every t value, this triangle is going to be camped here somewhere on this axis, and we're going to just compute the integral of their product. That's the definition of my convolution here. Again, you can see f2 of lambda is just sitting here. It doesn't change with t. So this integral is going to take place on my lambda axis, and it's going to be f2 multiplied by f1, and f1 is going to be shifted by whatever t says it should be shifted. So the integral is really just going to be related to the overlap between these two functions. So visualizing our integral, here we are at t equals 0. And at t equals 0, what I've done is, of course, I've just reflected this function around the axis, the vertical axis. So here it is. And so let's perform the integral. So as I do this integral, as I go along my lambda axis, which is what I'm integrating on, well, here f2 is equal to, f1 is equal to something, but f2 is equal to 0, so I got 0. And here, f2 is equal to something, but f1 is equal to 0, so at t equals 0, obviously the result of this integration is 0. So what let's do is let's plot that on the time axis. So as t increases, f1 slides right. Here it goes. The integral is the area shared by the function. And the full integration is performed at every value of t. We just performed the integration at t equals 0, and we got 0. So let's plot our first point. Here it is. So now, look at this. I can shift this all the way up to t equals 2, and I'm still going to get 0. So from t equals minus infinity all the way up to t equals 2, there's going to be no overlap. Let's plot that on our as a function of time. So we'll plot it on the t-axis. So take this triangle, slide it up to 2. Here it is, slid up to 2, and my answer is still 0. Why'd I stop at 2? I stopped at 2 because once I pass 2, then I'm going to get some overlapping area, and my result is going to start to go up. Let's do that. So again, here's my output or my time domain result. And I was 0 before t equals 2 because my triangle had not started overlapping. So now it's going to start overlapping. And I know that the length of my triangle is 1 unit, so I'm going to have to keep that in mind, right? So between 2 and 3, I'm going to increase my area because see how as I slide my triangle in here, the overlapped area is getting greater. So see it's starting to go up. But when I hit t equals 3, or in other words, the nose of my triangle is going to hit 3, Now my triangle is completely inside the other function. So at t equals 3, I end up here. Here's my scenario. And the overlapping area is going to be just 1/2 the base times the height equals 0.5. So see how in my output, when I get up to t equals 3, I know that my output is 0.5. Furthermore, I know that until that it is going to remain 0.5 as I slide this triangle along here, because the area is going to be the same. The overlapping area is the same. So I'll make my result line just camp here at 0.5 until we get up to t equals 5. What's going to happen at t equals 5? Well, we are going to start decreasing the amount of overlapping area because my triangle is going to start shifting out here. Let's look at that scenario. So t gets greater than 5 and my area is going to start to decrease. What's going to happen when when t gets to 6? Now the butt of my triangle is going to be outside of my rectangle and I'm going to have no shared area, and so my output is going to be 0. So this is a hand-waving graphical convolution. How accurate is it? Well, between 0 and 2, it's accurate. Between 3 and 5, it's accurate. Above 6, it's accurate. But this little wiggler in here, we just kind of waved our hands on that. Now what we want to do is do the exact same problem, but this time we're actually going to use integration. And what I might suggest at this point is that when I did the graphical example, it's pretty easy to get kind of mesmerized into the simplicity of the sliding triangle and the overlap. But there's a tremendous number of concepts that went into that before we got to that point. So if you're not really good on the concepts that allowed you to slide those triangles by, this might be a good time to stop the video, go back and actually review the stuff with the impulse response and the Laplace Transform Roadmap and how we did convolution by going across the top of our Laplace Transform Roadmap. But now, let's do the last example mathematically. So now the math. Below t equals 2, f of t is equal to 0 because we had no overlap on those functions. So that's enough math for me for that one. So now what let's do is let's do the section from 2 to 3. Now, why am I going to handle just the section from 2 to 3? Because that is where the nose of my triangle starts to overlap with the rectangle. And it'll start at 2, but once I get to 3, remember that my triangle will be all the way inside the rectangle, and so the function will change because the output's going to get flapped. So what we're going to start by doing is get this little wiggler right in here and get its mathematical function. So we're going to use the definition of convolution, and we're going to use that to set up our integral. And so First of all, here is our time-shifted and reversed F1. F1 of t and lambda is equal to t minus lambda. Go back to our shifting and reversing and make sure you're comfortable with this. Make sure that when I change t, that triangle just moves. Okay, so what let's do is let's set up our integral. And here it is. We know that our rectangle function is just a 1 between 2 and I think 5 or whatever it was. It's just 1. So the way I'm going to accommodate that, the way I'm going to get this shared area is I'm going to set my lower integration on the lambda axis to 2. Or in other words, the integration starts here. And where does the integration stop? It stops where the nose of my triangle is. And that's going to be t. So my lower integration limit is 2. And my upper integration limit is t. So here's the integral right here. So that's a fairly straightforward integral. I go through all that and I end up with this function right here. F of t is equal to t squared over 2 minus 2t plus 2. And that is valid from 2 is less than t is less than 3. So let's do a sanity check on that. So f of 2 is going to give me 2 minus 4 plus 2 is 0. That's good, because at f of 2, we know we're 0. F of 3, let's plug 3 into our formula. And we substitute that in and we get 1/2. So what we've done with our formula here is we've made a formula that gives us the overlapping area wherever this triangle is. That's why in our final answer here, t is still a variable, because this integration represents that triangle in one position. Or in other words, it's shifted by t, and t is a constant in this integration. Okay, so again, what that gave us was the overlapping area here. When we did the problem graphically, we kind of waved our hands and said, well, it's going to increase until the triangle gets all the way inside here, and then it's going to be 1/2 the base times the height, which is 1/2. So we said it's going to kind of wiggle its way up and end up as 1/2. And now between 3 and 5, see my triangle moving over? I know that it's going to remain at 1/2. And I don't need an integral to tell me that. So let's put that in here. For our next region, 3 is less than t is less than 5. In this region, f of t is just equal to 1/2. So here it is formally. F of t equals 1/2 for 3 less than t less than 5. You notice I'm a little cavalier here about maybe putting a less than or equals for one of these. I'm an engineer. That's what we do. Our next region is going to be the area between t equals 5 and t equals 6. Why do I have to handle that as its own region? Because below 5, my triangle is all the way inside here, and 1/2 the base times the height gives me 1/2. But as t increases past 5, my overlapping area will decrease. How do I handle that? Well, what I'm going to do is I'm going to use limits of integration again. Where's this point on the lambda axis? It is at t minus 1 because it's 1 below t, because that's the horizontal width of our triangle. So I'm going to start integration at t minus 1. And I'm going to finish my integration where the rectangle stops, and that's going to be at 5. So I'm going to integrate from t minus 1 to 5. And of course, you can see that when t becomes 6, I'm going to have no more overlapping area because the triangle will be just outside the rectangle. So what you're seeing here is I'm handling this rectangle just by using limits of integration. But what I'm really going after is just the overlapping area. So here is my function again. It's just t minus lambda. And remember, t is a constant as far as this integral goes. That's why I end up with a function of t. I integrate that out, and I get this function here. And as a sanity check, I substitute in 5, and I get a half, which is correct. I substitute in 6, and I get 0. And here is our function. I may have mentioned to you that my favorite tools are, I use a word processor, I use MATLAB, I use Excel, I use Visio. Those are my big tools. And I really like using Excel where I can. Now, I could have plotted this using MATLAB, but I didn't. And the reason I like to use Excel, especially in industry, is not everybody has MATLAB, and not everybody has to use MATLAB. So I like to look at my audience, and I look at where I'm sending something, and if it's going to some people that may not have MATLAB or may not use MATLAB, maybe because they're in a different department, or maybe they're old people like me and they don't know how to use MATLAB or whatever, everybody who has Microsoft Office has Excel. So I use the heck out of Excel, especially the goal-seek formula, which is under the data what-if analysis. It's one of the most useful things I know of. If I have one equation and one unknown, and it's a really nasty one, I use Excel's goal-seek to solve it. But what I did here is I said I've got a couple of different functions, and each one of these is a time point. I have a couple of different functions. I look at the result of each one, and then I use the if statement to determine what region I'm in, and out it pops. I'm 0 below 2. I am a half from 3 to 5, and I'm 0 above 6. So that's the exact plot. A lot of math. What are we really doing? Let's go back up here. What we have done is our impulse response in this case was the rectangular function. So we had this circuit where we put an impulse in and it went boink, boink, and down it went. We put an impulse in and it went up and then down. And into that circuit, I put in a little slice of a triangle function. So in went my triangle function, and we convolved it with the impulse response, and we got that nice little output that we showed in Excel. Let's take another look at our function that we just used. We just said that this was the impulse response. Of course, the problem was just convolve F1 and F2, but I don't do that. I got to have some significance. So I said, okay, F2 is my impulse response. F1 is my input. So F1 is my input. Aren't I really shoving that input through the filter? Doesn't the input go into the filter and then kind of go through, kind of slide through? Let's say this input is Beethoven's Ninth Symphony. So do you want out, Bella? You want out? All right. She just wants to meow. So let's say that I've got Beethoven's Ninth Symphony here. It starts here with a, sorry, that's Sixth Symphony. Okay, Beethoven's Sixth Symphony starts off with this nice stuff, and then it goes all the way to the end. But I want to shove Beethoven's Sixth Symphony through this filter. Doesn't it make sense that I'm going to put the first note through and the last note last? I mean, if I'm going to shove Beethoven's Sixth Symphony through a filter, I'm going to put the first note in and the last note last. So what am I going to do with that symphony? I'm going to turn it around, and I'm going to shove the first note in first and the last note in last. Here's the symphony. Here's the first note. Here's the last note. I'm not going to shove the last note into the filter. I'm going to shove the first note into the filter first. And that and that is going to explain to us why we reflect before we convolve. We're not going to put the last note in first. We're going to reflect it, and then we're going to put the first note in first. So let's look at our lambda axis. Our lambda axis is really kind of the guts of the filter. We can think of that as the guts of our system, or the guts of our system. I'm going to take my Beethoven's Sixth Symphony. I'm going to time reverse it. So the first note is here, and I'm going to slide it through that filter. Doesn't that make sense? So that gives you just kind of a intuitive idea for why you have the time reversal. Now let's say, why do we have this lambda axis that integrates out all the time? That is, think of that axis as being inside your filter. The lambda axis sits still in the filter while you shove the input signal past it. And of course, you time reverse the input signal, so the first part of the input signal will go through the filter first. So make sure you're good with these concepts, because you're going to forget how to do convolution integrals, but I want you to remember that concept, and we're going to work on that a little bit more. Let's do some practical convolution. We're in the middle of a lockdown right now, so I left my copper pipe in my office and I can't get in to get it. But what I have is a copper pipe. You could think of it as a little thing on a wind chime or something, where the little thing hits it and it goes ding, 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 ding. But I have just one, and I have a little piece of fishing line on it so I can hold it, and then I hit it with my pen, and it goes ding. So let's do that. We just don't have the pipe. So here's our little whack. It's an approximation to an impulse. That is me taking my pen and going tick. And here is the response of my copper pipe. This is its impulse response. Does that make sense? Well, here, we'll pretend like my architect's rule is the pipe, and I'm going to hit it with my whack. Ding! Ding! So, see it? Look. Ding! See the envelope going down? Ding! And of course, the period of this is going to be omega naught over 2 pi, because of course, the resonant frequency of the pipe is going to be omega naught. And by the way, it's an underdamped system because it goes ding. It doesn't go boom. If I took a beanbag, or if I took my calculator and go, I get a thump. So this is an overdamped system. Boom. But I take my pipe and it goes ding. And the omega naught, or the note that I am singing, the frequency of the note, is the natural frequency of that system. Now you might remember, let's just jump back to chapter 8 a little bit. All this is connected, folks. Listen. Ding. Oh, I think I'll hit it harder. Ding! Hit it gently. Ding! What's happening? The omega naught is the natural frequency of the system. By the way, it's also the resonant frequency of the system. And how hard I hit it? Ding! Ding! Those are my A2s and A1s that I get in chapter 8 with my initial and final conditions. It's all linked together. So you can see I took my whack and I hit the pipe and I got the experimental impulse response. Makes perfect sense. Ding! You knew that before this lecture. Now let's take that, which is easy, and let's make it hard. I'm going to strike the pipe a few times. So here I go. You can see my whack 1, whack 2, and whack 3. Ding, ding, ding. Ding, ding, ding. Duh, right? Let's do it with convolution. My input signal is going to be my whack, my x of t, my 3 whacks actually. So what am I going to do? Time reverse them. And you can see I've indexed them. This is whack 1, whack 2, whack 3. I'm going to time reverse them and put them on the lambda axis. Here they are. Here's whack 1, here's whack 2, here's whack 3. Well, duh, of course I want to put whack 1 in the system first. So now I'm on the lambda axis. I'm going to slide my whacks through. Okay, so you notice here, time started, bang. The starting gun goes bang, and then whack 1, whack 2, whack 3. So here, as I slide these through, nothing is going to happen until this whack hits my impulse response. So both of these are on the lambda axis. Here's the impulse response. It sits still on the lambda axis, but I'm going to slide my whacks through. And when the first whack goes in there, it's going to carve out this impulse response. And then as I keep sliding, whack number 1 is going to be over here, not really doing anything. But now whack 2 is going to hit my impulse response. And then it'll keep on sliding. And then whack 1 will be here, whack 2 will be here, and then whack 3 will hit it. And so to get that time domain function, I'm going to slide the input right and integrate as we go. Here's y of t. So here's our convolution integral. H of lambda is the impulse response. It's just sitting still on the lambda axis. X of t minus lambda is our whacks, and they are sliding past here as I change t. And the result of the convolution, well, whack 1 went through about this much time after 0. Hey, there's the result of whack 1. Here's the result of whack 2. And here is the result of whack 3. we took something simple. Ding, ding, ding. We used all the math that we've learned in this lecture, and we kind of made it complicated, but we got our simple answer that matched with our intuition. Now, in the next lecture, we're going to do stuff that is not going to be quite so intuitive, but we're going to use the exact same concepts. So I want you to really understand this example. So this time, I'm going to excite my pipe with a signal generator. And the signal generator is going to make little sine wave bursts. Or in other words, if I were to listen to the signal here, because I'm taking my signal generator, I'm going into a speaker, I'm going to hear right here. Right? Little sine wave starts up, then it stops. That's what the signal generator makes. Now what I'm going to do is I'm going to take my speaker and I'm going to glue a wood dowel to the cone of the speaker. And then I'm going to let that wood dowel strike my pipe. So what I'm going to do is I'm going to excite my pipe, which is hanging by the string, with this signal. And this is just kind of how I'm going to do it. So here's my input from the signal generator. You can see that it's got some frequency, and I'm showing it as a function of time. There, I sang it, or I whistled it. Now here's the impulse response of my pipe in the time domain. Remember, my pipe goes, it goes ding, ding, ding. So you can kind of see in my lame drawing here that it's actually kind of going out and dying down. You can see its envelope. So here's my input. Here is my system impulse response. So what we're going to do is we're going to put everybody on the lambda axis. My system impulse response just transfers right over. My two inputs, bung, bung. I'm going to time reverse them because, of course, I want the first one to go in and then the last one. So here's my time reversed input. Let's slide it through. And here is the response when the frequency of my signal generator is equal to the natural frequency of my pipe. Because you can see that when this thing slides through here and the frequencies are the same, think of the integration. These two things are going to be right on top of each other. Man, they're going to integrate up a party, right? And so it's going to make a huge signal. And so here's what it's going to look like. Because when this is on top of this, those frequencies line up. When this one is high, that one's high, big. When this one is low, this one is low. Two wrongs make a right, even more big. So I'm going to get this great big response in the time domain. Now let's say that I excite it at a frequency that is not equal to the natural frequency of the pipe. Well, now this is kind of be up, and this one will be down, and this one will be, and they're not going to line up perfectly. And let's look at the output. I'm going to get ding, ding. It's going to be a lot smaller. So what you can see here is, in this case, we excited the system at its resonant frequency, or its natural frequency, where it wants to vibrate. And of course, the system said, whoa, yeah. Here, we excited it at a frequency that was not its natural frequency, and it didn't respond very well. Here's an example. Let's put a little kid on a swing set. I give him a push, and the swing comes back, and I go, ooh, push him again. And it comes back, and do I push when the swing is still coming back up toward me? Of course not. It's going to hurt the kid, and it's not going to give me a very good push. So what I'm going to do is wait till the kid's butt comes back, and as the kid starts going down, I'll give him another push. They'll come up, they'll start going down. I'll push them again. Well, the swing set and the kid determine the natural frequency of the system. And I am exciting the system at the natural frequency. Let's say that instead of putting a kid there, I put a 60-pound bag of concrete on the swing, and I say, I don't care when that swing comes back. I'm going to push it once every 3 seconds. Well, I'm going to go, and all of a sudden, that swing set is really not going to be doing too much, is it? So more trapdoors in EE310. I'm saying we're exciting the system at its natural frequency and I'm getting a peak response. If I excite a series RLC circuit at its resonant frequency, I get the maximum amount of current. And so it holds true with copper pipes. And you can see that we did this as a convolution example where we took something simple that we could visualize intuitively. We used the math to describe it, and then we pointed at all these other areas of EE310 where it is applicable. Before we leave this lecture, I'd like to do one quick piece of review on taking Laplace transforms. So the example that I'm going to do is going from the time domain to the frequency domain. It goes back to our first lecture on Laplace transforms, but I want to use the properties to give you a better feel for using them. I know that a lot of students have trouble with combining the properties and the Laplace transform table. So I want to just throw this example. But again, where are we on the roadmap? Take a time domain function, put it in the frequency domain. So let's do it. So this is a problem right out of our book. And f of t is equal to 2e to the minus 4t times u of t minus 1. So that's a nice mathematical expression, but before I'm going to get too excited about using it, I got to plot it. I got to see it. And it's easy to plot because at t, if I didn't have the u of t minus 1, then I could just plot 2e to the minus 4t. And I'll say that at 0, obviously that's going to be 2, so I'm going to put a 2 up here. And then I'm going to go down to get the value at t equals 1. Why? Because that's where the function actually starts because of my unit step function. Remember, my unit step function goes 0, 1. So my function, as described here, is just this little thing, all the way down to 0. So let's make sure we know what it is at time equals 1. So at time equals 1, it's going to be 2 times e to the minus 4. Boy, it's not going to be too big, is it? So I certainly didn't do this to scale, but that's good enough for me. So probably the first thing I'm going to do is go look in my Laplace transform tables. And what I'm going to see is that this function is way too specific for the Laplace transform tables. But using properties and simple Laplace transforms, I can get the answer pretty easily. Or in other words, I need to break this up into the right Lego pieces. And to do that, I'm going to use properties. And the way I'm going to do it is I'm going to use the properties to get the simplest f of t that we can. and then I'll get the f of s, the Laplace transform of the simplest f of t, and then I'll apply the properties to get the final f of s. So in our 2 lectures ago, I showed a bit longer of an example, and I showed a little line going down the right-hand side that says, start with f of s, break it, or f of t, start with f of t, break it down, make it simple, make it simple, make it simple. Take a trivial little Laplace transform, apply the results, apply the results, apply the results, and then you get a big Laplace transform. So let's do that for this function. We have f of t is 2e to the minus 4t u of t minus 1. I'm going to start off by using the frequency shift property because it'll allow me to take this e to the minus 4t out. Now, just quickly, you say e to the minus alpha t, f of t is frequency shift, and it's just a good reminder for the fact that we are using complex exponentials, e to the j omega t. So that's just kind of a good thing to remember. So we're going to take this property, and that will allow us to drop the e to the minus 4t, and I'm going to say that my my f of t becomes just 2 times u to the t minus 1, because I know how to handle this e to the minus 4t in the Laplace domain. So I'm simplifying. My function is now 2 u of t minus 1. So here I'm going to use the time shift property. So f of t minus a times u of t minus a is just going to be e to the minus as times f of s. And so if I now pull my minus a out here, I'm going to end up with just 2 u of t, right? Just 2 u of t, because I'll handle that delay in the Laplace domain because of my property. So this is as simple as I can get. So now let's take our simple little Laplace transform. F of s is just going to be 2 times 1 over s. That's 2 over s. So let's apply the time shift of 1 second. Well, what I have to do is multiply my s domain function by e to the minus s, or e to the minus as, and a was 1. So I just multiply my simple Laplace transform by e to the minus s. Let's keep going. Now I have to apply the results of the frequency shift that I did up here. And what I'm going to do there is just change my Laplace transform. So wherever I see an s, I change it to an s plus a. So 2 over s plus 4, e to the minus s plus 4. And here is my Laplace transform of the function that I started with. Okay, so that's today's lecture. Lots of concepts, lots of pieces of this lecture. So make sure to go back and make sure you really do pick up these concepts. And I will see you all in our next lecture, where we're going to talk about the acoustics in sleazy bars with cinder block walls, all the way up to a beautiful 16th century church. And we're going to do some fun stuff with digital filters and music. And since we're going to be there, it's only going to take me just a little more time to show you how the mixing board works at the club. So you'll have something to talk about when you're in the club next time. You can look at the guy on the mixing board or the girl on the mixing board, say, hey, I know how that works. So I'll see you in that next lecture. As always, I look forward to seeing all my students at my office hour.